e la condivisione. Allora ragazzi, mi sentite e vedete il mio schermo? Bene. Allora, iniziamo la lezione di oggi. So let me start with introducing a new quantum number that is baryonic number. We have actually already introduced this number. Let's now go into some more detail. So the baryonic number of a state is defined as the number of baryons minus the number of antibaryons. But of course, we can translate these also at the quark level. So at the quark level, it corresponds to the number of quarks minus the number of anti-quarks divided by 3. And so if we now take this definition and use the following convention, so the baryonic number of a quark is 1/3 and the baryonic number of an anti-quark is minus 1/3, then it turns out that all baryons will have a baryonic number 1, all antibaryons will have baryonic number -1, and of course mesons and antimesons will have baryonic number 0 because they are made by a quark and an antiquark. Now, the important thing is that all known interactions conserve the baryonic number. So the strong, the electromagnetic, and also the weak interaction. And the best experimental limit for this baryonic number conservation comes from the search for the proton decay. So let's spend now a couple of slides about the search for the proton decay. So the proton today, of course, is supposed to be a stable particle. Okay. However, there are searches to search for very rare events where the proton might decay to some other final state. And in particular, the lower limit on the lifetime of the proton has been measured through the so-called, to this baryonic number violating decay, where the proton decays into a positron and a pi 0. Okay. And based on these studies, the present estimate, or let's say lower limit of the lifetime of the proton is 10 to the 34 years. In this sense, we expect the proton is in fact a stable particle. So with essentially an infinite lifetime. Now, 10 to the 34 is, if you pay attention, 24 orders of magnitude larger than the age of the universe, which is, is order of 14 billion years, okay? Now, to reach such level of sensitivity, one needs to control something like 10 to the 34 protons for several years and to be ready to detect the decay of a single proton in case it would happen. And so far, this has never been found, okay? Now, the searches for ultra-rare events have to be carried out in virtually background-free environment, of course. For the proton decay search, the main source of background is coming from cosmic rays. Okay, and so the best way for shielding cosmic ray is, as you know, to work in deep underground laboratories. Now, one example of those laboratories is the Super Kamiokande detector in Japan. You see here a picture. Okay, so this is a huge tank filled by water, and all the walls are covered with photomultipliers. And this detector has been built and widely used for the study of neutrino physics. In particular, they discovered for the first time the neutrino oscillation phenomenon. Okay. Now, the important point for what concerns now us is that this detector contains 22,500 tons of water, and this corresponds, water is made by hydrogen and oxygen, so this corresponds essentially to 7.5 10 to the 33 protons. So this is the number of protons you expect when the full Super Kamiokande detector is filled with water. And so now we reach a huge number of protons, okay, which is comparable with what you want to have in order to study the proton decay. And in fact, the Super Kamiokande is the ideal place to look for proton decay events. Now, how the searches actually proceed? So people is searching for this decay here. So the proton into a positron and a pi 0, okay? If this decay would occur, then the positron that is emitted in the final state will produce a Cherenkov light into the water. I guess you know what Cherenkov light is. Do you know?
Yes, we do.
Yes, we do.
Okay. Yes, fine. Then also the pi zero decays immediately into 2 gamma. The gamma convert into electron-positron pairs, and those also produce another Cherenkov light. Okay, so you know that Cherenkov light is emitted along a cone, okay, with a certain opening theta related to the refractive index and the velocity of the particle. And once this cone intercepts the wall of the detector, you observe this as a ring, okay, a ring of light essentially. And this light is captured by all these photomultipliers. So the Cherenkov light forms a ring in the array of photomultipliers, and the event is recognizable through its specific topology of rings, so of reconstructed Cherenkov rings, okay? Okay, so far 0 events have been observed, okay? Now, back to our story. So last time we have defined the strangeness quantum number of a hadron as the number of strange quarks minus the number of anti-strange quarks, and all overall with a minus sign on top of this. Now, another useful quantum number that is indeed very useful for the classification of hadrons, essentially for those containing up, down, and strange quarks, is the hypercharge, or if you like, the strong hypercharge. We will see also there is another different hypercharge, which is the weak hypercharge. So hypercharge is defined as the sum of the baryonic number that we just defined and the strangeness number. Now, since the baryonic number is conserved in all interactions, it turns out that hypercharge is conserved only in those interactions that also conserve strangeness. That is, it is conserved in strong and electromagnetic, but not in weak interactions. We have seen last time that weak interaction violate strangeness conservation. And this is the reason why the lightest strange hadron can only decay to the weak interactions, as we have seen. Now, of course, the hypercharge of mesons coincides with the strangeness, because for mesons, as we've seen, the baryonic number is exactly 0. Now, there is a way to relate these quantum numbers with the third component of isospin, and this is the Gell-Mann-Nishijima relation, which is written here. So the third component of isospin is given by the electric charge minus the hypercharge divided by 2. And then you can further split the hypercharge into the baryonic number and the strangeness number. Okay. We will do an exercise on this. Okay. Now that we have collected enough information about isospin, strangeness, and baryonic number, let's now work out some problems. So the first one, problem 5.4. The sigma star plus is an unstable hyperon with a mass of 1,385 MeV and decay width of 35 MeV. It is produced in the strong reaction, K minus proton into pi minus sigma star plus, and it decays into a pi plus lambda 0 with a branching ratio of 88%, so with a very high probability. Now, the first question, is the decay into a pi plus lambda 0 regulated by the strong electromagnetic or weak interactions? The second, why the analogous reaction, where now you are swapping the kaon charge and the pion charge, okay? Why this, let's say, partner reaction does not actually occur in nature? And using the fact that the lambda 0 baryon is an isospin singlet, determine the isospin of the sigma star plus. Okay, let's move now to the board, and let's try to solve this. Okay, pagina 1. So let me start with, this is a problem 5.4. Let me start with point A. Okay, so here the question is whether the interaction that regulates this decay is strong, weak, or electromagnetic. So we proceed in the usual way. Okay, so we know that the lifetime is given by h bar divided by the decay width. We multiply by the speed of light. So that in the numerator we know that this is approximately 200 or 197 if you want to be more precise. MeV times Fermi, and then we divide by the width which is provided, which is 35 MeV times the speed of light in Fermi per second. So 3 10 to the 23rd Fermi per second. And so the result of this is order of 1.9 10 to the minus 23 seconds. So it is an extremely short decay time, as you can see. And so, of course, this means that the decay must proceed through the strong interaction. As we have seen, the decay time of regulated by electromagnetic and weak interaction are much, much longer. Okay. So strong interaction, this means that strangeness and isospin must be conserved. Must be conserved. Okay. Now let me move to the question B. The question B was to evaluate. Let me go back to the text. Why the analogous reaction, okay, when we swap the charge of kaons and pions does not occur in nature, okay? So as we've seen, the sigma star plus is creating the strong reaction K minus proton into pi minus K star plus. Okay. So the strangeness of the sigma star baryon, since the pion has no strangeness, the strangeness of the sigma star baryon must be the same as that of the kaon. So the only strange particles here are the kaons and this sigma star. Okay, protons and pions come with zero strangeness. Okay, so the strangeness of this strange baryon must be the same as that of the kaon because strangeness is conserved in this strong process. So what about now the kaons? So we know that the K minus is a U bar S object and that the K plus is instead a U S bar object. It is the antiparticle of the K minus. Okay, so from this we learn that the strangeness of the sigma star plus must be the same of the strangeness of the K minus. The K minus has a strange quark, okay, so it comes with the strangeness -1. Okay, so by imposing strangeness conservation in this strong reaction, we made a prediction of the strangeness of the sigma star plus. Now, why the other process is forbidden? The other process was the K plus proton into a pi plus sigma star plus. Okay. The problem, of course, is that in this case, strangeness would not be conserved because now the strangeness in the initial state is the strangeness of a K plus. But now the K plus comes with an S bar. And the strangeness of an S bar is +1. And so this is different than the strangeness of our sigma star baryon. That is instead -1, okay? So in fact, in this case, we have a delta S equal to 2. We have a violation of strangeness of the order of 2. And this is the reason why this strong reaction cannot occur, okay? Now the last point. The last point was using the fact that the lambda 0 baryon is an isospin singlet, determine the isospin of this sigma star plus. So now we have to study the decay of this baryon. So the sigma star plus goes into pi plus lambda 0 as it is given in the text. Now, as we know from the text, the lambda 0 is an isospin singlet. So it comes with an isospin 0. And then by isospin conservation, because this is again a strong decay, the isospin of the sigma star plus can only be given by the isospin of the pion. Okay, and we know that the pions form an isospin triplet, so they come with isospin 1. So it turns out that the isospin of the sigma star plus must be equal to the isospin of the pion, that is 1. And in fact, it turns out that the sigma star is a member of an isospin triplet, much like the pions. So the members of this triplet are in fact the sigma star minus, which is a down-down strange object, a baryon, the sigma star 0, that is a UDS baryon, and the sigma star plus, that is a UUS baryon. So you see here that The isospin of the strange quark is 0, and then we have a minus 1/2, so 1/2. So this comes to be exactly 1. 1 here and 1 there. Okay. So let me summarize what you've seen here. So first of all, by taking using the information of the decay, we realize that the decay of this object must be regulated by the strong interaction. Then strong interactions, of course, conserve strangeness and isospin. And by imposing strangeness and isospin conservation in this process, as well as in the reaction, we obtain the isospin and strangeness quantum number of this strange baryon. Ok, andiamo adesso al secondo problema. Chiaro, ragazzi?
Sì, però sì.
Ok. Allora, problema 5.5. Verify that the following hypothetical decays of the omega minus baryon conserve electric charge, baryonic number, strangeness, and third component of isospin. So we have 3 decays, omega minus in proton, 2 K minus and the K0 bar, or in lambda 0, K minus K bar 0, or in Xc0 K minus. Okay, and the additional information we have is the quark content of all these objects here, okay, and their masses. And then the second question is actually why all these decay are actually forbidden, okay? So let's first solve the first part of the problem. Let's move back to the board. Okay, so this page 2. So we have to check that electric charge, baryonic number, strangeness, and third component of isospin are conserved in this decay. So the best way to do so is to construct tables like this. Okay, so let me start with the first one. That is the omega minus that goes into proton plus 2 K minus plus K0 bar. And so we make a table like this. We have the charge, the baryonic number, the strangeness, and the third component of isospin. Now here we have the initial state, where we have our omega minus, and then here we have the final state, where we have, in this case, the proton, the 2 K minus, and the K0 bar. And then we can also take the total quantum numbers for the final state. And then we can even check if there is a match or not. Okay, so let's start with electric charge. Electric charge of the omega minus is clearly -1. Okay, what about the final state? We have a +1 for the proton, twice -1 for the kaon, and 0 for the K star. So the overall total electric charge of the final state is -1. This corresponds to the initial state, so we have a match here. Electric charge is conserved. What about baryonic number? The omega minus is a baryon, okay, so it comes with a +1 baryonic number. In the final state, we have a proton, which is, of course, a baryon. Then the kaons are all, as you remember, mesons, okay, so they have both 0 baryonic number. So overall, the final state baryonic number is +1, and again, we have a match between initial and final state. What about strangeness? So we know that the omega minus is an SSS baryon, a baryon made by 3 strange quarks. So the strangeness is -3. Now we move to the final state. So the proton, of course, has no strange quark, so it comes with 0. The kaons have 2, -1. They both come with a one single strange quark. And then the K0 is another -1. So overall, we have -3, and also here, the strangeness is conserved. And finally, the isospin. So the omega does not contain any up or down quark, so its isospin, the third component, is 0. What about now the final state? We know it is +1/2 for the proton, then it is twice -1/2 for the K minus. They contain a U bar quark, antiquark, and a +1/2 for the K0, which contain a up quark. Okay, so overall, again, we have 0, and we have, again, a perfect match. Okay, so all these quantum numbers are conserved in this decay, in this hypothetical decay of the omega. Let's now do the same for the other. So we'll continue this table here. So now, here we have, for the second reaction, second decay, we have still the omega minus here, and then we have the lambda 0, the k minus, and the k0 bar. Then we have the tot here. And still we have to check the same quantum numbers. So the charge, baryonic number, strangeness, and I3. Okay, so we start again. The charge is, or the omega minus is -1. The lambda 0, it is a neutral particle, so it's 0. The k minus is -1, and the k0 is, of course, 0. So we have a -1, and again, we have a match. Now the baryonic number, this is, as we know, a +1. Then we have a +1 for the lambda 0, which is, in fact, a baryon, UDS baryon in particular. Then we have a 0 for the two mesons. And so +1, okay. Strangeness, this is a -3. It is a SSS baryon. Now, the lambda 0 is an UDS baryon, so it comes with one strange quark, so its strangeness is -1. And then same for the two other kaons. So we have -3, again, perfect match. And finally, the third component of isospin, which is 0 for the omega, as we have seen. It is also 0 for the lambda 0, which is an isospin singlet, as we have seen also in the previous problem. Okay, and then here we have anti-up quark and an up quark here, and so we have 0. Okay, so again, perfect match for all quantum numbers also in this hypothetical decay. And now let me go through the last one. So we have still the omega minus. And now we have the psi 0 and the k minus. Oh, okay, so for the omega is always the same. It is -1, +1, -3, 0. Now, the psi, the charge is 0, okay, is psi 0, and the charge of the k minus is -1, so the total is -1, and we are happy. Baryonic number, the psi is a baryon, so we have +1. The k minus is a baryon, is a meson, so we have 0. And so overall +1, and we are happy. Strangeness, the psi, is a double strange particle. It comes with two s quarks, so the strangeness is -2. We have another strange quark in the k minus, so this is -3, and we are again happy. And finally, third component of isospin. Okay, we have an up quark here, we have an anti-up quark here, and so overall is 0, and overall is fine. Ok, chiaro?
Sì, sì.
Ok.
Sì, tutto chiaro.
Okay, so we are in a solution, in a condition in which all these three decays conserve at least these four quantum numbers: the charge, baryonic number, strangeness, and third component of isospin. However, we know from the text that they are all forbidden. So can you try to think now why these decays are forbidden? Look at the information you have in the text. Let me go back to the text.
Could it be related with the mass?
Yes. So try to be more specific.
It was just a guess. Now I just thought it. It seems that the products of for the first reaction, the products have a much smaller mass than the omega minus particle.
A larger mass, not a smaller, a larger.
Larger? Yes, it's larger.
Mm-hmm. And this is indeed the problem. So exactly, if you sum the mass of the final state particle, so the product of this decay, you end up with a mass which is larger than the one in the initial state, the mass of the omega. And this means that, and this actually you can check for all three decays. This means that essentially energy would not be conserved in this decay. Okay.
Mm-hmm.
So this 3 decay would produce an energy violation, and this is the reason why they cannot indeed happen. Okay, regardless that they conserve the main quantum numbers. And in fact, let me go back to the backboard. Okay, the only possible decays for the omega baryon are regulated by the weak interactions, and these are the following. So the real decay of the main 3 decays of the omega are the following. So a psi 0 pi minus with a branching ratio of order of 23.7%. And in this case, we have in the initial state a strangeness of -3, in the final state a strangeness of -2, and so you have a delta S equal to 1, okay? And so this, of course, can only occur through the weak interaction, because weak interaction is the only one that can violate strangeness conservation. Then for the second possible is the omega minus into xi minus pi 0. Here the branching ratio is order of 8.6%. And again, we have in the initial state, the strangeness is -3. In the final state, it is -2. So again, we have a delta S equal 1. And the third most likely decay for the omega minus is into a lambda 0 K minus with a branching ratio of 67.8. And again, strangeness in the initial state is -3. Strangeness in the final state is -2. And again, we have a delta S equal 1. Okay. So these are the 3 most probable decay of the omega. Of course, they all are regulated by the weak interactions. And it is also clear because the omega is a 3-strange quark baryon, and it is the lightest baryon with 3-strange quark. So it cannot decay strongly in a lighter baryon with 3-strange quark. It can only decay to a lighter baryon with a smaller number of strange quark, and so you expect to have a strangeness violation, and so this can only occur through the weak interaction. All right, let's move on to the other. 5.6, find at least one conservation law, invariance principle, or other mechanism responsible for suppressing or forbidding the following decays. Okay, so we have a k plus into pi plus, pi 0, k plus into pi plus, pi minus, pi plus, pi minus, pi plus, pi 0, lambda 0 into k0, pi 0, xi minus into a neutron pi minus, and here we have also the information about the isospin and the quark content, and then the pi 0 into 3 gamma. Okay, so let's start from the first one. So this is, that was problem 5.5. Give me one moment. And this is the problem 5.6, and we are in page 3. All right, so let me start from the first one. K plus into pi plus, pi plus, pi 0. Can anyone tell me immediately why this reaction is forbidden?
The charge is not conserved.
Exactly. So the initial charge, of course, is +1. The final charge is 1 plus 1 plus 0, that is +2. So charge would not be conserved, and the charge is conserved in all processes. So this is the reason why this reaction is not possible. Let's move to the second one. So we have a k plus into pi plus, pi minus, pi plus, pi minus, pi plus, pi 0. So let's check first of all the charge. In initial state it is +1. In the final state we have +1, -1, +1, -1, +1, +0, that is +1, which is okay. It is equal to the initial state. So charge conservation is not the problem here. What is the problem then? Try to think.
Strangeness is not conserved.
Strangeness is not conserved, but in principle, this is fine if the decay is a weak decay. Okay? So there is a more fundamental reason why this can never happen in any kind of interaction.
Energy.
Forse ancora per le masse.
Esatto, è ancora per le masse. The mass of the initial state is the mass of the K plus, that is a little bit less than 500 MeV. And the mass of the final state is essentially 6 times the mass of a pion, that is order of 840 MeV. That is greater than the initial mass, okay? So the problem here is that the mass is not conserved. Actually, this process is energetically impossible, okay? It would violate energy. Now, third decay, we have now a lambda 0 into a K0 pi 0. So the charge is clearly conserved. The mass is also fine because now the initial state mass is the mass of the lambda, that is 1115 MeV. Whereas the final state, we have the mass of the kaon plus the mass of the pi 0, that is overall 633 MeV. It is smaller than the initial state mass, so this is okay. So what goes wrong here?
Is it the baryonic number?
Indeed, yes. In the initial state, we have a baryon, that is +1. In the final state, we have 2 mesons, that is 0 plus 0 equals 0. So baryonic number is not conserved, and this is the reason why this decay can never occur in nature. Let's move now to the fourth. So we now the psi minus into a neutron plus a pi minus. So charge is trivially conserved, -1, and then in the final state it's 0, -1, it is -1, which is fine. The mass is also okay. Initial state is the mass of the psi minus. It is 1322 MeV. And the mass in the final state is the mass of the neutron plus the mass of the pi minus. That is 1080 MeV. That is smaller than the initial state mass, so energy is conserved. What about baryonic number? Initial state, we have a baryon, that is +1. And in the final state, we have a baryon plus a meson, that is still +1. So baryonic number is okay. So what can be now the problem? This is a little bit more.
Maybe,
sorry?
Maybe strangeness. Strangeness.
Strangeness is not conserved, yes, but still this can occur in a weak decay.
Still, okay, sorry, yes.
Okay.
Like the other.
Okay, yes. So let's move step by step. Let's check now with the isospin. Okay, initial isospin is 1/2. For the final isospin, we have the isospin of the neutron by the isospin of the pi minus, and then we have the sum of the two. That is 1/2, 1/2 minus 1, 1/2 plus 1. And so the two possible values of isospin are 1/2 and 3/2. So in the initial state, you have 1/2. In the final state, you have 1/2 and 3/2. So in principle, the decay can occur even strongly through the common value 1/2. Okay. Let's now look to the third component of isospin. In the initial state, you have -1/2, sorry. In the final state, you have to sum up the the third component of isospin of the neutron, that is -1/2, and of the pi minus, that is -1. And it is now -3/2. And this is different than third component of isospin of the initial state. Sorry, this is I. Okay. In particular, since the final state we have 3/2. Okay, this means that the isospin in the final state can only be 3/2. It cannot be 1/2, right? So this is different than the initial state. So clearly, isospin is not conserved, so the process cannot be nor strong nor electromagnetic, but only weak. Okay, and in fact, if you now check the strangeness, let me go here. The strangeness of the initial state is -2. We have 2 strange quark. The strangeness of the final state is 0. You don't have strange quark in the neutron and the proton. And so we have now a delta S equal 2. Okay. So this is consistent, of course, with the weak decay. However, the problem is that this is anyway a strongly suppressed weak decay, for the reason that we will study in the future, because it requires a so-called flavor changing neutral current transition. So we need, in order to have this kind of decay, you need a transition between the strange and the down quark, and the strange and the down quark come with the same electric charge. Okay. But of course, there is a change of flavor from the strange to the down. And as we will study next, when we will study the weak interaction, this is a case of flavor changing neutral current transition, which is highly suppressed anyway, also in weak interaction. And in particular, it turns out that the branching ratio, let me go here, the branching ratio of this decay is in fact extremely small, is less than 1.9 10 to the -5. So it is not forbidden, it is allowed. It is a delta S2 decay, but it is highly suppressed. And the reason we will study better next in the future. Now, let me change page. Ok, questa è la pagina 4. Now we go to the pi 0. That goes into gamma, gamma, gamma. So let me go fast here. So the charge clearly is conserved, 0 and 0. The mass, of course, is fine. We have the mass of the pi 0 that is 135 MeV, and the final state mass is 0 because we are dealing with the photons. So this is fine. Energy can be conserved. Baryonic number is 0 in the initial state and also in the final state. It is fine. Strangeness is 0 in the initial state and in the final state. It is also fine. Isospin. In the initial state, we have 1. In the final state, we have 0. So isospin is not conserved. Okay, but still this is okay for electromagnetic and weak process. Right? Clearly, since you have photons in the final state, this cannot be a weak process, but in principle could only be an electromagnetic process. Okay. What about the third component of isospin? I3I is 0. Okay, it is the intermediate particle, intermediate pion in the pion triplet. And for the final state, we have, of course, 0. Okay, so I3 is conserved, which is still okay for an electromagnetic decay. Okay, so what else? We can check parity. The parity in the initial state is -1. We know that pions are pseudo-scalar mesons, so they come with a negative parity. In the final state, we have -1. We have 3 particles, so L12 plus L3 times the intrinsic parity of the photons, which is -1 per each. So we get here an additional minus sign. So this is -1 L12 plus L3 plus 1. So the final state parity is equal to the initial state parity only if the total angular momentum, so L12 plus L3 is even. Okay, then you get a minus sign also there. So still this is possible. So far we couldn't find a reason why this decay is forbidden. Now try to think yourself. Any idea?
No idea.
No idea. Okay.
For the charge
So-
conjugation,
Sorry? Say again?
for charge conjugation.
Exactly. Charge conjugation is the problem. You're right. So in the initial state, we have the charge conjugation of the pi 0, which is an eigenstate with eigenvalue +1. For the final state, we have the -1 to the third, if you remember, for a system of n pions, so of 3 pions in this case, that is -1. And this is the problem. So charge conjugation not conserved. And this is a problem because we are now looking for an electromagnetic process, okay? And charge conjugation must be conserved in any electromagnetic process. If it would be a weak process, then this was not a constraint. But since we selected as the only possible mechanism an electromagnetic decay, then charge conjugation must be conserved. And this is, in fact, the only reason why this decay is forbidden in nature. Okay, great. Let's move to the last one. So using the Gelman-Nishijima relation, check that the third component of isospin assignment of the following hadrons is correct, essentially. So back to the blackboard. This is problem 5.7. This is page 5. Now, the Gelman-Nishijima relation that I showed before relates the third component of isospin with the electric charge and the hypercharge. So for a system made by up, down, and strange quark, this is just baryonic number plus strangeness number divided by 2. So you have to check this if we obtain the correct values for the third component of isospin. So the first in the row was a proton. So electric charge of the proton is +1 minus. The proton is a baryon, so baryonic number is +1. There is no strangeness here. We have 0, so it is 1 minus 1/2, that is +1/2, which is exactly what we expect for a proton as a third component of isospin. What about now the antiproton? This is the charge now is -1. The baryonic number is -1. Again, we don't have strangeness, so this is -1 plus 1/2, that is -1/2. Again, this is fine. We know that the third component of isospin of the antiproton is the opposite of that of the proton. Okay. What about the neutron? E3 neutron, the charge is 0 minus. Baryonic number is +1. We don't have strangeness. We divide by 2, so it is exactly -1/2. Again, is what we want. Now let's move on to the lambda 0. The charge is 0. It is a neutral baryon. So being a baryon, now we have a +1 baryonic number, and also it is a strange baryon, okay, with an S quark. So we have a -1 for the strangeness. And so overall, this is 0. And in fact, we know that the lambda is an isospin singlet. That means that I is equal to I3 is equal to 0. Now let's look for the K plus. So the charge is +1. Baryonic number is 0 because it is a meson. The strangeness is +1, we divide by 2. So it is 1 minus 1/2 equal to +1/2. And it is okay. You know that the K plus is a US bar meson. So having an up quark, it must have a positive 1/2 assignment. And last one, the sigma plus, it is +1 minus, it is a baryon, it is a strange baryon with strangeness -1, we divide by 2, so this is +1, which is also fine. The sigma plus is a up strange system, so you see here that the isospin must be 1. All right. Ok, se non avete domande su questa parte, cominciamo ad andare oltre.
No.
Tutto chiaro?
Va bene, possiamo andare avanti.
Ok.
Sì.
Allora, adesso cominciamo a introdurre il modello a quark. Okay? Quali sono state le ragioni alla base, quali sono poi anche le conseguenze e le verifiche sperimentali. Okay, so this table summarized the particle discovered up to, let's say, 1947, so before the 1950s. Okay, that is before particle accelerators went into operations, the first particle accelerators. So all the discovery were either obtained by cosmic rays, okay, studies, or through simple low-energy nuclear reactions. So the electron was discovered in 1987 by Thomson, through cathodic tubes. The proton and the neutron were discovered in 1999, 1932 by Rutherford and Chadwick through these two nuclear reactions. And then we have a bunch of other particles that have been discovered in the 30s and 40s, again through cosmic rays searches. So the positron we have studied in detail. It was discovered by Henderson with the cloud chamber in 1932. Then also Anderson discovered a few years later the muons that were originally confused with the Yukawa particle, if you remember. Then finally the Yukawa particles, or the pions, were discovered by Occhialini et al. In 1947, okay, still in cosmic rays. And then also in 1947, the Rochester-Butler experiment that we also discussed provided the first discovery of strange particle, and in particular of the kaons. So this was the situation, let's say, up to 1950. It was rather simple. Only, let's say, dozen of particles were discovered at that time. And since particles were so few, the particle known at the time, it was also, let's say, legitimate to think that these objects were all elementary particles, okay? So point-like without any structure inside. Now, troubles came in the following years, in the 50s and 60s, when the particle accelerators come into operations, and also the bubble chambers, okay? And in fact, it turns out that in a matter of few years, okay, order of 100 new particles were discovered, okay? Here only some of them are shown here, okay? So it was a kind of revolution. And this put, of course, the physics community into a crisis, because now how can you justify nature to provide 100 different elementary objects? This makes no sense, okay? And in fact, it was soon realized that hadrons having the same JP quantum numbers could be grouped into multiplets, into the hypercharged third component of isospin plane, okay? And now, since you have this kind of regularities, this essentially was suspected to be the manifestation of some internal degree of freedom of this object. And so, in the sense that these particles, these hadrons, must not be elementary object as originally thought, but they must have some internal structure, some more fundamental structure inside, okay? And this aspect soon evolved into the quark hypothesis, okay? Sostanzialmente, diciamo, è quello che successe 100 anni prima con la tavola periodica degli elementi, no? Fino alla fine dell'Ottocento si conoscevano ancora pochi elementi e quindi, vabbè, man mano che gli elementi furono scoperti, Mendeleev scoprì che c'erano queste regolarità, okay? Queste periodicità, e questo fu infatti l'indice, diciamo, il campanello d'allarme per capire che in realtà gli atomi in realtà non sono oggetti elementari, non sono oggetti puntiformi, ma hanno una struttura in termini di protoni, neutroni, elettroni, e da lì chiaramente si andò avanti. Quindi è lo stesso tipo di ragionamento e di crisi si ebbe in realtà per quanto riguarda le particelle negli anni 50-60, ok? Now, the quark model. So the quark hypothesis, so-called also the static quark model, was proposed independently by Gell-Mann and Zweig in 1964, who in fact provide an elegant solution to the puzzle. So according to their proposal, hadrons are composite system made by elementary objects that we call now quarks, which carry a fractional electric charge. Okay, so until 1974, only 3 quarks flavors were known: the up, the down, and the strange. And so the original quark model, of course, only included those 3 quark flavors. So the up quark comes with the fractionary charge of 2/3 of the electron charge, and the down and the strange minus 1/3, as you know. And according to the model, quarks are subject to the strong force and form bound states with integer electric charge in 3 different ways. So they can arrange into baryons made by 3 quarks, antibaryons made by 3 antiquarks, and mesons, as you know, made by a quark and antiquark. Now, the correspondence between the experimentally observed hadrons and those predicted by the quark model, of course, constitute one of the strongest arguments for the existence of quarks. Let me show now this nice picture. So this is Gell-Mann, who passed away less than 1 year ago. And this is it was his car, and look at the plate here. Funny guy. Now, the regularities of the observed hadrons can be understood in the framework of the quark model and find indeed a physical justification in the so-called flavor symmetry of strong interaction. This is at the basis of the quark model. Okay, so strong interaction treat all quark flavors equally, and therefore the strong Lagrangian possess an exact flavor symmetry. Okay, so the strong interaction between quarks is independent whether they are up, down, or strange. What matters, of course, is the color charge, the color degree of freedom that we will study next in QCD. Now, we've seen already the isospin symmetry, and the isospin symmetry is in fact a manifestation of a more general symmetry, that is the flavor symmetry, that generalize the isospin symmetry that only apply to up and down quarks. Okay. Now, in the case of isospin symmetry, this symmetry is almost exact because the difference in mass of the up and down quark is very small, and also the difference in mass between the proton and the neutron, okay, compared to the mass of hadrons. So, and the electromagnetic interaction, which is the only responsible for this mass difference, indeed represents a small contribution to the overall interaction Lagrangian. So we can split the total Lagrangian into an, let's say, free particle Lagrangian and an interaction term, which we can further split into the 3 elementary interactions. And as we know, the strong is strong, okay? It's much stronger than the electromagnetic and the weak, okay? And this is the reason why the isospin symmetry is such a good symmetry, okay? Now, in principle, it is possible to extend the isospin symmetry to a more general symmetry that also includes the strange quarks. So not anymore up and down, but up, down, and strange. And this is what we call, in fact, the flavor symmetry. There is, of course, a problem now, because now the mass of the strange quark is order 96 MeV. And it is very different than the mass of the up and down quarks, okay, which are order a few MeV. So the overall Lagrangian now, L tot, is manifestly not flavor symmetric, okay? The difference is too large, okay, to make the same arguments we did for the isospin symmetry. However, if you now compare the mass of the up and down and the mass of strange, okay, with the typical mass of baryons, which are larger than 1 GeV, then the mass of the strange quark is still reasonably small, and so we can still reasonably assume that the overall Lagrangian possesses an approximated up-down strange flavor symmetry. It is clearly less exact than the isospin symmetry, but still a reasonably good one. Okay, so it is more approximated by the isospin symmetry, but we can still use this symmetry to make predictions. And in fact, predictions then turned out to be in very good agreement with the experimental results, as we will see. So now we have to extend our formalism that we introduced for the isospin to include also the strange quarks. Okay, so to extend our isospin symmetry to this more general flavor symmetry. Okay, the flavor symmetry can be expressed by unitary global transformation in the flavor space, given in this way. Okay, but now the dimension of this transformation is higher. Okay, So again, alpha I are now 8 global parameters. They don't depend, of course, on the space-time coordinates. And these lambda I are the corresponding generators. And these generators are conventionally chosen to be the 8 Gell-Mann matrices that you find here, which are 3 by 3 matrices, and which essentially describe a generalization of the 3 Pauli matrices when you now work in this 8-fold space. Okay. Now, these 8 independent unitary traceless matrices form a fundamental representation of SU3 group, much like the Pauli matrix form a fundamental representation of the SU2 group, as we have studied. Now, the dimension of the group is 8 because it is n squared minus 1, as we studied in general, okay? And this symmetry is called the Flower symmetry, so it is denoted as SU3 Flower or simply SU3F. What about now the relation between the Gell-Mann matrices and the Pauli matrices? So the SU3 Flower group contains as a subgroup the SU2 isospin group. Okay, and in fact, if you look now at the first 3 Gell-Mann matrices, lambda 1, lambda 2, lambda 3, they have the Pauli matrices inside, okay, in the top left 2 by 2 block, where all the other elements are vanishing, okay? So this, in a sense, tells you why these the Gell-Mann matrices represent an extension into a larger dimensional space of what we already studied in the 2-dimensional space with the Pauli matrices. The remaining Gell-Mann matrices can be identified by realizing that the SU3 group also contains the other quark SU2 quark exchange, so up to strange and down to strange, okay? Both of which can also be expressed in terms of the Pauli matrices. Okay, so this just to give you that we are now working in a larger group, and the SU2 group for the isospin symmetry is a subgroup of this more general Flower SU3 group. Now, we can proceed, of course, in the same way, okay? So as we've done for the isospin in SU2, now we can also define the basis vector for this fundamental representation in SU2 Flower, which are now the Flower triplets, okay? For the isospin, we had the isospin doublets. Now we have the Flower triplets. So up is 1, 0, 0, down is 0, 1, 0, and strange is 0, 0, 1. And it turns out that these are simultaneous eigenvectors of lambda 3 and lambda 8. And the corresponding eigenvalues are related to the third component of isospin and to the hypercharge through the following operator. Okay, so the operator T3 is essentially 1/2 the third Gell-Mann matrices, and the hypercharge operator is 1 of square root of 3 of the 8th Gell-Mann matrices. And let's check now this. So this is page 6. So for the third component of isospin, T3, the operator is 1/2 of the third Gell-Mann matrices, and for the hypercharge, this is 1 over square root of 3, and then we have the 8th Gell-Mann matrices. So let's apply now the first operator to the up quark state. So this is 1/2, 1, 0, 0, 0, minus 1, 0, 0, 0, 0. And then we have our up quark eigenstate, that is 1, 0, 0. Okay, so now you make the matrix vector multiplication and you obtain exactly 1, 0, 0, so exactly plus 1/2 up. Okay, so the up quark is eigenstate of third component of isospin operator with eigenvalue plus 1/2, as we know. Let's now work out this for the down quark. The matrix is the same, 1, 0, 0, 0, minus 1, 0, 0, 0, 0. Now we apply to 0, 1, 0, that is our down quark state, and we obtain 0, minus 1, 0, that is minus 1/2, 0, 1, 0, that is minus 1/2 d. And we know that the third component of isospin for the down quark is indeed minus 1/2. Now we apply this to the strange quark. 1, 0, 0, 0, minus 1, 0, 0, 0, 0, 2, 0, 0, 1. And once you do that, you obtain 1/2 and then the null vector, 0, 0, 0, that is 0. And in fact, as we know, the strange quark has clearly 0 isospin. Let's now work out the hypercharge operator. So we start again from the up quark. That is 1/√3. Now the Gell-Mann matrix come with the 8th Gell-Mann matrix come with another 1/√3. And then we have 1, 0, 0, 0, 1, 0, 0, 0, minus 2. And this you apply to our up quark state. And you will find 1/3, 1, 0, 0, that is plus 1/3 of the up quark. So it turns out that the hypercharge of the up quark is exactly 1/3. And then we repeat with the down quark. Okay, you do yourself, and at the end we find also here 1/3 for the down quark. And in fact, the hypercharge of the down quark is plus 1/3. And finally, we apply to the strange quark. You can check this, and you will find at the end a minus 2/3 for the S quark. And so the hypercharge of the S quark is in fact a minus 2/3. Ok, direi possiamo fare una pausa di qualche minuto, ricominciamo alle 10:20. Anzi, fatemi prima dire una cosa, prima di fare la pausa fatemi soltanto tirare un po' le fila. Ok, andiamo avanti, diciamo un paio di minuti solamente. So these eigenvalues are obviously in agreement with the values provided by the Gell-Mann-Ishijima relation. Okay, you can check yourself when you use 1/3 for the baryonic number of the quark, then the proper electric charge of the quark and also the proper strangeness of the quark. You can just try here, substitute it with exactly the same results. Now, this table summarized indeed what we have found. Okay, so we have the up, down, and strange quark. They are the spin, baryonic number, electric charge, third component of isospin, strangeness, and now hypercharge. Okay, these are the values that we just calculated. And we can represent these numbers, okay, these actually quark or flavor triplets in this plane where you have here the third component of isospin and hypercharge. Okay, so the up quark has 1/2 isospin and 1/3 hypercharge. The down quark has minus 1/2 for the isospin and still 1/3 for the hypercharge. And the strange quark has 0 isospin and minus 2/3 of hypercharge. What about now the antiquarks? For the antiquarks, I3 and Y quantum numbers have opposite sign. It's like electric charge, okay? So they swap sign. So when we now want to represent the antiquark flavor triplet in this hypercharged third component of isospin space, then now the strange quark comes here. So it still has 0 isospin, but now the hypercharge is plus 2/3, and then up and down will swap in this way, okay? So we know that now the third component of up quark is minus 1/2 for the isospin and plus 1/2 for the down, anti-down, and both still come with now minus 1/3 for the hypercharge. Ok, fermiamoci qui e continuiamo, riprendiamo alle 10:20, 5 minuti. Ah, aspetta, visto che siete adesso tutti o quasi tutti, vi chiedo conferma, quindi per il venerdì dalle 9 alle 11, se va bene a tutti, fare una terza lezione settimanale di questo corso a partire da febbraio. Vi confermate tutti o qualcuno ha problemi che non ha ancora detto?
No, per me va bene come l'ho detto
Sì,
prima.
Per me va bene.
Ok. Rigiro la domanda, c'è qualcuno che ha problemi per venerdì 9-11 per tutto il mese di maggio? Ok. Allora, mi sembra che siamo tutti d'accordo. Chiederò adesso poi a Michele Gambetti se può aggiungere questa lezione, poi vi farò sapere via mail. Ok?
Ok,
Va
va
bene.
bene.
Ok, dai, facciamo 5 minuti di pausa, riprendiamo alle 10:20. Ok ragazzi, mi sentite? Possiamo riprendere? Allo?
Sì, io la sento. Non so io.
Ok, va bene. Allora riprendiamo adesso da qui. Okay, so we have just seen how to represent the quark triplet and the anti-quark triplet into this space. That is a plane made by the hypercharge and the third component of isospin. Okay. Now, let's now go into more detail on how to classify and represent mesons. So today we will deal with mesons. Tomorrow we will move to baryons. Okay, based on the quark model. So these are now the quark flavor triplet and the anti-quark flavor triplet that I just showed in the previous slide, okay? Now we want to construct mesons. So we want to construct a bound state of a quark and anti-quark. And so as we've done already for the isospin symmetry, we have now to combine a quark triplet with an anti-quark triplet. And when you do so, okay, in group theory, you will obtain an octuplet, octet if you like, and a singlet. And these are essentially the flavor, the quark flavor component of these objects that you find. Okay, so the 8 octet states transform among themselves under the SU3 flavor rotations, but do not mix with the singlet state. Of course, this is only true if the symmetry is assumed to be completely exact. And we know already that the symmetry is not exact, it is only approximated. Okay. So much like the way you swap from up quark and down quark with the isospin symmetry, you now can swap through all these components of the octet based on the SU3 flavor transformations or rotations. Okay. Now the singlet state, which is represented here, is a UU bar, DD bar, SS bar state, corresponds to 0 hypercharge, 0 isospin. So in fact, it comes in the origin of this plane, and can be thought as a flavorless state, essentially carrying no information about flavor and its constituent, okay? Because X flavor is annihilated by the anti-flavor, as you see here. Now, mesons are bound states of quark. Sì?
Posso fare una domanda precedente? Non ho capito, nel grafico dove vediamo l'ottetto, perché nella rappresentazione ci sono solo 7 punti.
Sì, allora, ce ne sono 2 qua dentro, che okay. I flavor non sono indicati, ma sono 2 in origine. Okay, li vedremo meglio tra un attimo.
Ok, va bene. Avevo il dubbio,
okay. No, hai fatto bene a alzare la questione. Sì. Li vedremo meglio tra un attimo, adesso qua non sono rappresentati, ma questo cerchietto qui sta a indicare che c'è altra roba qua dentro. Ok?
Va bene, grazie.
Allora, now mesons are a bound state of quark and anti-quark, so QQ bar system. Each quark anti-quark, as we know, has 2 possible spin states. So the total spin of the meson can be either an S0 singlet or an S1 triplet, as we know. Now let's concentrate ourselves to the low-lying states, so only the lightest mesons which have 0 orbital angular momentum. Okay, so for those states, the total angular momentum, which is L plus S, since L is 0, is just equal to the spin. Okay, and therefore for the lightest mesons, one can only have these 2 angular momentum combinations, so either J equals 0 or J equal 1 states. What about parity? This we have seen already. So the parity for a meson is -1 to the L, and then the intrinsic parity of quark and anti-quark. Here you gain another minus sign because quark and anti-quark have opposite intrinsic parity. So it is given to -1 L plus 1. But now, since we are focusing ourselves only to the low-lying states with L equals 0, if you put a 0 here, you get a minus sign. Okay, so all the low-lying states must have negative parity. Okay, and the possible angular momentum assignment are again either 0 or 1. So considering all possible combination of flavors and spin, one obtains 9 light JP0 minus mesons, which are so-called pseudoscalar mesons, okay, and also 9 JP1 minus vector meson, vector because now the angular momentum is 1, okay. Each category being composed by an octet and a singlet. So let's now see this in more detail. So these are the JP0 minus octet states, and these are the JP1 minus octet states. Okay, so let's start from this one. Here we see in the central row the 3 pions, pi minus, pi 0, pi plus, which indeed form an isospin triplet. So we have 3 states. Then we have the 2 isospin doublets, which is the K0, K plus, and the K minus, K0 bar, okay, which come with either plus or minus isospin symmetry, yeah. And we have an analogous, and then we have another object here, which is eta 8 that we will discuss later, okay, which comes with 0 hypercharge and 0 third component of isospin. Then we have, let's say, a copy of this, but now for vector mesons, okay, so spin total momentum equal 1. We have now, so the 3 pions are now replaced by the 3 row mesons, okay. If you check now, the quark content is exactly the same, okay, but these are now vector mesons, so they come with spin 1. And then we have now these K star mesons, okay, which again form 2 other isospin doublets. So in total, what we see here is 2 isospin doublets, 1 isospin triplet for each of the 2 systems, 1 isospin singlet, eta 8 or phi 8, and then in total we have 2 states with 0 hypercharge and 0 third component of isospin. That is the eta 8 and the pi 0 and the eta 8 and the rho 0. They both stay here in the center, okay? And then we also have the singlet, okay? And the meson singlet, as by definition, is a 0 isospin and 0 hypercharge state, okay? Now, let's now consider these 2 guys here, the pi 0 and the eta 8, okay? So the pi 0, yeah, is a member of this triplet, and eta 0 is a singlet, isospin singlet. So they both have 0 third component of isospin and 0 hypercharge, okay? And this is their flavor content. So is UU bar minus DD bar for the pi 0 and UU bar DD bar minus 2 SS bar for the eta 8. So far, so good. For the singlet, okay, for the case of pseudo-scalar mesons, okay, the corresponding state is called eta 1. So 1 stands for singlet and 8 stands for octet, okay? So these objects belong to the octet, these objects belong to the singlet. This is the reason for this notation. And now the flavor content of this guy is, of course, a completely flavorless object. So UU bar plus DD bar plus SS bar, as we've seen, okay? Now, what is the problem here? These 2 objects, so the eta 1 and eta 8, are not observed in nature. So they are predicted by this flavor symmetry, by the quark model essentially, but in fact they are not observed in nature. And the 2 observed E30 and hypercharge 0 states are instead named eta and eta prime. And these eta and eta prime mesons corresponds to linear combinations of the eta 8 and eta 1. Or if you like, to a mixing of a singlet and an octet state with these quantum numbers. So the real observed mesons in the octet are now those that I've seen before, and now this combination eta and eta prime, which are a combination of these 2 unobserved singlet states. Sorry, the singlet state and the other with the 0 quantum numbers. Now, of course, mixing octet state with a singlet state would not be possible if SU3 were an exact symmetry. If this were exact, you can have any kind of transformation within the octet, but you can never mix octet state with singlet state. You can do, in fact, nature does, and the reason is that the flavor symmetry is not an exact symmetry, okay? For the reason that we've seen before, okay? There is a huge mass difference between the strange quark and up and down, so it is only an approximated symmetry. And the correct description of these complicated mixtures of quarks and antiquark pairs and gluons can only be understood in the framework of QCD, okay, which is now, of course, the gauge theory of the strong interaction, okay. That came, of course, afterwards, the formulation of the quark model, the static quark model. So if, in addition, the SU3 flavor symmetry were exact, then the E pi 0 and the eta mesons would have had exactly the same mass. However, since we know that the symmetry is broken, okay, the quark of the strange quark is much larger than the mass of the up and down quark, okay, then it turns out that also the mass of the pi 0 and the mass of the eta are quite different. So the pi 0 we know is 135 MeV, and the eta meson is order of 550 MeV. Okay, and what about the eta prime, the other combination? This is much heavier, so order of 1 GeV almost. And the reason of that can only be understood again in the framework QCD, but not in the framework of this simplified quark model. Okay, we will come back to the mass of the mesons later on. Now, these are now the vector mesons. Okay, and here the situation is even more complicated, even worse if you like. So in the case of the vector meson, the mixing between the 0 state of the octet and the singlet, okay, the phi 8 and the phi 1, is even more pronounced than for the pseudoscalar meson. Okay, so this is the quark flavor, the quark flavor of the F1 and F8, which are not observed in nature. Okay, as we have seen for the eta 1 and eta 8. Instead, these two vector meson combination are observed in nature, the phi meson and the eta meson, which are again combinations of the phi 1 and phi 8. Through these, you can see these essentially as a mixing angle, so as a rotation in this space. Okay, and the mixing angle is quite large in the case of the vector meson. It's over 35 degrees. It's a large angle, where it is quite smaller, only 11 degrees for the case of the pseudoscalar meson that we have seen before. So the mixing is even stronger for the case of light mesons, of vector mesons. Now, the observed state are with the E30 and hypercharge 0 are then the following, okay, concerning the vector meson. So the rho 0, UU bar minus DD bar, the omega, UU bar plus DD bar, and the phi, which is an S bar state, okay? And if you now look at the quark, so this explains why the omega and the rho, sorry. This explains why the omega and the 70 or 80 MeV, and the mass of the phi is something like 300 MeV heavier, okay, because now we have to take into account that we have two strange quarks here. So all this order of 1 GeV. Now, this table summarizes more or less the main properties of the pseudoscalar mesons, okay? So on top we have the 3 pions. Here you see the lifetime. For the charged pion, we know that this is a quite long lifetime, so this can only decay weakly, okay, into muons and neutrinos, or positrons and neutrinos. And the pi 0, okay, we have a decay time typical of electromagnetic processes, and in fact it decays electromagnetically in a 2 gamma with an extremely high branching ratio. Then we have the kaons, so the 2 charged ones and the 2 neutral ones. The naming K short and K long, this we will understand later on in the course. Okay, we will discuss later on why they are called short and long. They all decay weakly. Okay, you see here now the branching ratio of the main decay processes, and these are the lifetime. They are all quite, you see, quite long, so typical of weak decays. And then we have the eta and the eta prime, and they decay actually electromagnetically into pions or photons or whatever. Okay, eta. Now, this is the corresponding table for the vector mesons. Okay, so we have now the rho, the K star, the omega, and the phi. Now, the lifetime here are very, very short, so they are typical of strong interactions. Okay, and so the decay with this branching ratio in either 2 pi or K on pi or 3 pi, etc. Let me just point out this last line here. So the decay of the phi into 2 kaons or 3 pions. So if you look now at the diagram for this decay, okay, you can represent it in this way. So the phi meson is an S-bar meson, as we have seen, okay? And this is the way it can decay into a K plus K minus pair. And this is the way it can actually decay into a pion triplet, pi plus, pi 0, pi minus. Now, you see that the branching ratio of these two channels is very different, and it is much more favorable for the case of the kaons. However, if you now look at the available phase space for this decay, okay, for the case of kaons, it is much, much smaller, because if you adapt the mass of the kaons, you almost obtain the mass of the phi. So you have only a very small mass residual that allows you for a small phase space for this decay. Whereas, if you now sum up the mass of the 3 pions, you obtain a much, much wider phase space for the decay. Okay, so the Q value is order of 600 MeV. So from the pure kinematical point of view, you would expect the decay into the 3 pions were much, much more favorable. Okay, if you consider, for instance, the Fermi golden rule, you have a much, much higher density of final state here than there. However, the opposite is observed. And this is due to the so-called, this is a suppression, of course, rule called the Ozzy rule, that we will see more in detail when we will study the QCD. Okay, so we will study then why this decay, despite the much larger phase space, is actually suppressed. Okay. Now some more details about the mass of the mesons. Okay, so the measured mass of the ground state mesons are reported in this table. So here they are the pseudo-scalar mesons, and these are the vector mesons, and you see here the value of the masses. Now, what can we learn from this? Of course, if the SU3 flavor symmetry were exact, all states in the pseudo-scalar meson octet would have the same mass. Okay, and clearly the observed mass differences derives from the fact that the quark strange is significantly more massive than the up and down quark, and this we know already. Okay, so the symmetry is broken, and in fact you have here quite different masses inside the octet. Okay. Now, however, and this you see, in fact, both for the pseudo-scalar meson and also for the vector meson. However, this does not explain why the vector mesons are more massive than the pseudo-scalar mesons. If you now compare these masses to these masses here, you see that all these guys are heavier than the corresponding pseudo-scalar mesons. Okay. For example, the wave function of the pions and the rho, as we have seen, is the same. They have exactly the same quark content, but they have a very different mass. Okay, the mass of the rho is something like 600 MeV larger than that of the pion. So why? What is the only difference between pseudo-scalar meson and the vector meson? Clearly, the only difference is the spin. Okay, in one case we have spin 0, in the other case we have spin 1. And in fact, the different masses of the pions and the rho mesons, and in general of the element of the pseudo-scalar octet with those of the vector meson octet, can be attributed to a spin-spin interaction term in the potential, which is known as the chromomagnetic interaction. Let's now study this. So the chromomagnetic interaction depends upon the relative orientation of the quark and the anti-quark spins. You see here there is a scalar product between the spins of the two, okay, Si times Sj. And it corresponds to a spin-spin term into the quark-anti-quark potential of this form here. Now we have a constant. Alpha S is the coupling constant of QCD that we will be studying, of course, at the proper time. Then we have the scalar product, we have the mass, of course, of the two quark and anti-quark entering into the game. And then we have the scalar product of the spin. And finally, we have also this delta function, okay, which ensures that this potential term is only large at short distances. So when x is equal to 0. When x is very far from 0, this delta function kills everything. And essentially, we don't have any more this chromomagnetic interaction term. Now, a similar effect, okay, is already observed in quantum electrodynamics, and it is indeed the one responsible for the hyperfine splitting of the energy level of the atomic hydrogen, as we have studied already, okay? But there is a fundamental difference because as we will see, the coupling of the strong interaction is much, much larger than the fine structure constant, which is the coupling of the electromagnetic interaction. So for the alpha electromagnetic, we know that it is order 1 divided by 137, whereas for the alpha strong, it can be as large as almost 1, okay? And so essentially the physics is the same, but now this coupling term is much stronger. And so in the case of strong interaction, the chromomagnetic interaction is much, much larger than the corresponding effect in QED. And it is so large that, in fact, it is the responsible for the big differences in the mass between pseudo-scalar mesons and vector mesons. And we now see why in a moment. So the chromomagnetic potential, due to this delta function here, vanishes at large distance. So it is only relevant for L equals 0 systems. Because if you now compare the orbitals, or the wave function, if you like, for different values of the orbital angular momentum, you see that only the S wave, so the L equals 0 function, has a non-zero probability, actually has a maximum probability in the center, okay? So at distance 0. Whereas if you move now to L equal 1, L equal 2, you see that at 0 you have a node, okay? So the probability to find quark and antiquark close enough is essentially 0. That means that this chromomagnetic interaction is only relevant for L equals 0 system, so the low-lying state mesons that we studied already. Now, what happened now? For an L equals 0 meson formed by a quark and antiquark of masses m1 and m2, the meson mass can be obtained through this phenomenological formula. So what we have here? We have the mass of the first quark, the mass of the antiquark, okay? And then we have this term here, where we have a constant parameter A, which has to be determined experimentally. There is no way to predict this, but you can fit your experimental data and get a value for A, which is essentially proportional to the alpha strong and the wave function, so the probability to find the quark and antiquark at 0 distance, okay? That is the place where the chromomagnetic effect is indeed relevant. So let's see now how can we work out this formula for the case of vector meson and pseudoscalar mesons. So let's move on to the board. Qui si è sconnessa, mi servirà qualche secondo per rifarla ripartire. E dai. Vediamo se parte. Temo di no. Vabbè, fatemi riavviare un attimino sta affare. Ok, ci siamo, forse. Ok, ce l'abbiamo fatta. Allora, so in order to calculate this phenomenological formula, we have to, and to distinguish between the pseudoscalar mesons and vector meson, we have to compute the scalar product of the two spin. Ok, so questa è pagina 7. So the total spin is clearly S1 plus S2, where 1 and 2 refer to either the quark and the antiquark forming the meson. So we take now the square. The square is S1 square plus twice S1 dot S2 plus S2 squared. Okay, we don't need the cross anymore here. So we can now derive from this the scalar product of S1, S2, and this is given by 1/2 S squared minus S1 squared minus S2 squared. And so the expectation value, this is what we need, S1 scalar S2, is given by the expectation values of these operators. So it is S squared minus S1 squared minus S2 squared, and that we can compute in terms of the corresponding eigenvalues, spin eigenvalues. So it is 1/2 S plus 1 minus S1 plus 1 minus S2 plus 1, where S1 is equal to S2 is equal to 1/2. We are talking about quarks, so elementary fermions. And the total spin, okay, can be 0 for pseudo-scalar, mesons and 1 for vector mesons. Okay, so we can now compute this expectation value for the two cases. So the S1 scalar S2 for the pseudo-scalar case will be 1/2. Then we have 0 for the total spin minus 1/2 times 3/2 minus 1/2 times 3/2. That is 1/2 minus twice 3/4. That is minus 3/4. And the expectation value for the scalar product in the case of vector mesons, vector meson, is 1/2. And then we have now 1 for the total spin minus, 1 times 2, 1 times 2, S plus 1, minus 1/2 times 3/2 minus 1/2 times 3/2. That is 1/2, 2 minus twice 3/4. That is 1 minus 3/4. That is 1/4. All right. So let's now substitute this into our phenomenological formula. And this is what we obtain. So for the case of pseudo-scalar meson, we substitute our minus 3/4 result, and this is the formula to use to calculate the mass of the pseudo-scalar mesons. And for the vector meson, this is the formula with the plus 1/4 here. Okay, so the masses of the spin 0 pseudo-scalar mesons are predicted to be smaller of those for the spin 1 meson because we have a different term with an opposite sign here, a different correction term, if you want. So you are summing here something, you are subtracting here something, and this is the reason why the mass of the pseudo-scalar are smaller than those of the vector meson. This only applies again to low-lying mesons, so L equals 0 mesons, where the chromagnetic interaction effect is substantial. Now, let's now compare the calculated value with this formula with the experimental value. So here we have the calculated value for our pseudo-scalar and vector meson, and these are the corresponding measured values. And you see that the agreement is very, very good. Okay, and it is highly surprising. Okay, that this simple phenomenological formula that do not take into account any QCD dynamics describes already so well the mesonic spectrum at the level of 1% or even better. Okay, and this was one of the first unexpected success of the quark model. Okay, so you are just you are not using QCD here. Okay, you're just or essentially only in a very simple way, as we will discuss in the next slide. But nonetheless, you obtain incredible agreement with experimental data. The only exception is the eta prime, which is not reported here. Okay, where the prediction is only 355 MeV. Okay, and the experimental value is let's say 3 times as more. Okay. Now, the reason for this discrepancy is attributed to the fact that the eta prime meson is a flavorless state, essentially. And as such, it can in principle mix with possible pure gluonic flavorless bound state, something that people call the glue balls, okay, and which discovery is still questionable. So there have been many searches in the last decades for glue balls, which are bound state of pure gluons, so completely flavorless object that can mix together with the wave function of this eta prime. But the experimental result is quite ambiguous so far. But this is predicted by QCD, okay? So it is, of course, still possible, and this might explain this large mass prediction here, mass difference. Now, be careful, because the strong agreement between the measured masses and the quark model prediction is obtained by using the following values of the mass into the phenomenological formula. Okay, so this is the A parameter, okay, the one that best fits the data. But then for the up, down, and strange quark, we have to use these huge masses. Okay, this is a 300 MeV for the up and down, and 400 MeV for the strange quark. Now, what does it mean? These quark masses are, of course, very different from the bare quark masses that we have seen being of the order of a few MeV for the down and 96 MeV for the strange quark. So up and down strange quark. Okay. Now these bare masses are known as the current masses, and as we will study, these are the masses that quarks receive by interacting with the Higgs field. Okay, this we will study at the end of the course. However, the masses that you see here and the mass that you actually need in order to obtain the experimental value from your phenomenological mass formula are much larger. These are called the constituent masses and represent the masses of quark now dressed with the cloud of gluons and virtual QQ bar pair originating from the QED interactions. Okay, so in a sense, the QCD is not yet used here in this very elementary model. Nonetheless, it is somehow taken into account because you are not considering your quarks as free objects inside the proton, but you are considering them in, let's say, a QCD-like environment, where inside hadrons, you know that you don't only have the 3 valence quarks, but you have also infinite gluons and infinite quark-antiquark pair that comes up from the vacuum, and so they're created and annihilated continuously. So if you dress now your bare quark with this dressing made by gluons and virtual QQ bar pairs, then it makes sense to have these large values here, and these are exactly the values you need in order to reproduce your experimental values of the masses. Okay. Now, the distinction between the current and constituent mass, let me reply to one more, implies that only 1% of the mass of the proton is attributable to the real mass of the quark. So if you sum up these 2.2, 4.7, etc. More, and so this is the mass that you obtain essentially through the Higgs mechanism. You only have up and down quark, of course, in the proton, okay? But the remaining mass of the proton, which is approximately 1 GeV, okay, arises actually not from the Higgs mechanism, but from the energy associated with the internal QCD gluon field. Okay, let me now conclude with a simple exercise. So here we need to calculate the mass of the following mesons using the phenomenological mass formula based on the chromomagnetic interaction by using this value for the constituent quark masses. So 370 MeV for the up and down quark, assuming that they are the same, and 490 MeV for the strange quark, and this value for the A parameter. So we have pions, charged kaons, neutral kaons, rhos, K star 0, and phi. We go here. Quindi questa è la pagina 8. This is problem 5.8. Okay, so let me write down the data of the problem. So mu equal to md, the constituent quark masses is 307 MeV. For the strange quark, this is 0.490 GeV. And then the A parameter to be used is 0.06 GeV to the cube. Now, let me also write down the phenomenological mass formula that we derived. So for the pseudoscalar mesons, this was M1 plus M2 minus 3A divided by 4 times M1 times M2. And for the vector mesons, this was M1 plus M2 plus A divided by 4 times M1 times A2. Okay, so let's start with the pions. So we know that the pi plus is a UD bar object, and that the pi minus is a U bar D object, and they are JP 0 minus mesons, so pseudoscalar mesons. Now, the mass of the pion, we apply now the phenomenological formula, is the mass of the up quark plus the mass of the down quark minus 3A 4 times the mass of the up times the mass of the down. Now, since the mass of the up and the down are assumed to be the same, okay, this is approximately equal to twice the mass of the up minus 3A divided by 4 mass of the up quark squared. So now we can substitute the numerical values. So we have twice 0.307 GeV minus 3 times 0.06 GeV to the cube, and then we have here 4 times 0.307 GeV squared. And the result is 0.136 GeV, to be compared with the experimental value, it is 0.139.6 GeV. So a very good agreement based on a simple phenomenological formula. Now let's do the job for the kaons. Now the K plus is a U S bar, the K minus is a U bar S, is the antiparticle. They are also pseudo-scalar mesons. So we apply the same formula. So the mass of the kaon must be mu plus now ms, we have now a strange quark, minus 3 times A divided by 4 mu times m1 times, okay, U and strange. So you now substitute the values. So 0.307 GeV plus 0.490 GeV minus 3 times 0.06 GeV to the cube. Then we have now the mass of the Hub quark and the mass of the strange quark in GeV. And the result is 0.498 GeV, to be compared with the experimental value of 0.494 GeV. Again, a surprisingly large, good agreement. Okay, the K0 you can do yourself. Let's move on now to a vector meson case. So let me change page here. So we move now to the case D. Okay, the K0 you can work out yourself. So the case 0, now we have vector meson, so the rho plus minus, with the rho plus being a U d bar and the rho minus being a U bar d, much like the pi plus and the pi minus. But now these are vector mesons, so JP1 minus. So the mass of the rho is equal to the mass of the up plus the mass of the down plus A divided by the 4 times mu times md. So now we're using the other formula, the one for vector meson. We substitute the values, so it's twice 0.307 GeV plus 0.06 GeV to the cube, 4 times 0.307 GeV squared. The result is 0.773 GeV, to be compared with the experimental value 0.775 GeV. Again, a striking agreement. And then we can also skip now E and F. You can do yourself, okay, for the K star and the K star 0. And let me just jump to the case G of the phi meson. The phi meson is an S bar, as we have seen, is a vector meson. And so for the mass of the phi meson, we have the mass of the S plus the mass of the S plus A, 4 times the mass of the strange to the squared. That is twice 0.490 GeV plus 0.06 GeV to the cube divided by 4 times 490 GeV squared. That is 1.032 GeV, to be compared with the experimental value of 1.019 GeV. Again, a very good agreement. Ok, per me ci possiamo fermare qui. Domande, dubbi?
No, grazie.
Ok. Va bene, noi continuiamo poi domani alle 11. Oggi abbiamo trattato i mesoni nell'ambito del modello a quark, domani tratteremo i barioni. Ok? Avremo la funzione d'onda del protone e anche lì vedremo come applicare le masse, queste formule fenomenologiche per le masse. Va bene. Ci vediamo domani allora.
Arrivederci.
Arrivederci.
Va bene.
Arrivederci. Arrivederci.
Arrivederci.